Hello, 8th grade math students, and it is Friday, May 1st, the last month of this school year. Yes, that is true. All right, let's get down to it. We're going to be doing the problem section solving of topic 7. And so let's see here. I want to go to digits. There we go. It says a model rocket rises quickly and then slows to a stop as it reaches its maximum height. Do you realize that when you throw something up in the air, if you had a radar gun on it, it would read 0 when it's at its vertex, at its peak? Yeah. Until the parachute opens, which it falls slowly back down, drag the tile. So we need the rocket to be taking off from the ground, climbing very, very rapidly. So I'm wondering if this one would go here. Ooh, looks like it hits the origin. That's a good thing. Now I need to continue that. Let's see. Oh, I don't think they quite line up, do they? Maybe. They might. Let's see if this one goes in the right spot. Do you notice these are all on the rise, so I can't choose any of those. Okay. Ooh, that's looking pretty good. And the last increasing one. And now we have to start decreasing. Okay, and notice it is making a parabola. We've talked about parabolas before, how it's a curve, a U-shape, and that is the way things rise and fall on Earth, parabolically. In fact, I think it's going to be on any planet with gravity. All planets would have gravity. Some could have a low amount of gravity. Okay, now here is where the parachute's going to open. Now the parachute is going to allow the rocket to not totally defy gravity, but it will catch the wind or the air and it'll cause it to fall at a more constant rate. I don't know if you realize this, but when you drop something, it doesn't fall at the same rate. When you drop something, it starts falling. Its initial velocity is 0, but then it speeds up the longer it falls if we're neglecting air resistance. Yeah, the parachute is going to account for air resistance. It's going to suck air into it, and therefore it's going to fall at a constant rate. Can you see this? How this part of the graph is linear. Yeah. So we had a parabola going on because, look, it's super fast, slowing down, slowing down, slowing down, slowing down, 0, speeding up, speeding up, speeding up, speeding up, speeding up. Oops, I didn't mean to move that, sorry. Then when we get here, now it's the same speed. See, it's covering the same height, same distance, this vertical distance, in the same amount of time, here and here and here and here, before it finally impacts the ground. Okay? All right, one more problem I want to look at, and it is hidden right here. It says, you walk home from school, stopping at a friend's house on the way. Sketch a graph to describe the total distance you walk during the time you walk home. All right, now we're not doing the distance from home, we're doing the total distance walked. So we're going to start off at 0 because we haven't walked anywhere yet. And so we're going to walk home. We're going to walk home from school, stopping at a friend's house. So perhaps we walk this distance, and now we're at a friend's house, and we hang out there for a while, and then we go, oops, I better get going home. And now we walk the remaining distance home. So there's going to be several possible answers, but it could look something like this. There we go. Okay, and notice I made this one a little steeper, but we were traveling at a faster rate. So maybe you were hurrying up to get to your friend's house right after school. You guys were running home, running to his house. Then you hung out for a little while, and then you just took a normal pace back to your house. Something like that. These are the kind of things you're going to be doing on tonight's homework. Okay, it shouldn't be too bad. It's just applications of what we did in all of topic 6. So that's it for this video. Mr. Lawrence signing off. Have a good day, everybody.